I'm the lead architect at TextUs. I'd normally say TextUs just up the road in Boulder, but it's not the case anymore. We don't really have our office. We've gone fully remote. We got people all over the country and even a few outside it. We're hiring just like everybody else. And I'd like to point out that this is a version of a similar talk I gave at the local Boulder Ruby group about 2 years ago. And if you listen to the Ruby on Rails podcast last week, you heard this glowing review from Jason, who works with us. Also, one of the co-hosts of the podcast, Brittany, is our engineering lead. She wasn't able to make it to the conference, but most of the rest of the team, including Jason, is here, and they're right over there. So if you want to talk to anyone after, there they are. If you hear any heckling, it's probably them, so you just ignore it. They'll be disciplined after the talk. All right, fair warning, this talk is going to be pretty detailed and code-heavy, so we'll just jump right into it. Like most everybody, I came to Ruby by way of Rails, and I've been doing it for over 15 years at this point. In the early days of Rails, there was the problem of where do I put all my business logic? All we knew at the time was MVC, model, view, and controller. Your business logic clearly didn't go in the view, so it had to go in the model or the controller, right? And that was the big debate in 2009, fat controllers or fat models. The Rails way for a long time was just put it all in your models. And if you had something that involved multiple models, it went in the controller. If you had to reuse it in multiple controller actions, then you put it in a helper. Luckily, I think it's accepted in Rails specifically and web application development in general these days that there's a huge variety of service objects. Each serve a specific purpose, and that's where you put all your business logic. Plus, the non-Rails frameworks like Hanami fully embrace having tiny objects that serve a specific purpose. As Rails got more popular, it was clear that fat models wasn't a good solution because you ended up with a huge mess of unmaintainable and potentially dead code in there. Some more forward-thinking Rubyists started exploring and adopting code design patterns found in other languages and then blogging and giving talks about it. Oftentimes, they reference patterns defined in design patterns known as the Gang of Four book or Patterns of Enterprise Application Architecture by Martin Fowler, often shortened to POEAA. These patterns were mostly tailored for C++ and Java, and most of them just completely unnecessary in a flexible and dynamic language like Ruby. But there's a handful that work extremely well in Ruby and Rails, and you probably used a few of them without realizing it, or you use a gem that implements one or more of them. If you haven't seen it yet, refactoring.guru is an amazing resource that details a bunch of these service objects and more general code patterns, and they have sample code in Ruby. A large portion of the site is even dedicated to refactoring code examples, like I have this gnarly code. You can refactor it with this pattern, and in the end code, yours looks like this. I strongly recommend checking it out. I reference it several times a month. It's great for like, I've got this gross code. I think there's a pattern, but I don't remember what it's called. And I can go find an example and match and get it all cleaned up. The library we're going to be talking about, Dry.rb, is an extremely powerful implementation of the command pattern. You can usually recognize the command pattern in Ruby as an object that defines a call method. Not always. It's common to see a command object that has one or a few public methods named as verbs. Here we have a fairly simple one. We can initialize it with some config, inject some dependencies, and then call it with some arguments, and hopefully it'll do something cool. A good application of the command pattern might be the steps required to authenticate a user. Here we have some code that you might find as a helper method in a Rails controller to decode a JWT token and find the user in the database. First, we decode and verify the token. Then we look up the user by the token. We add the user that we found to some context like error tracking or analytics. And then finally, we return the user. So let's extract that code into a command object. Here's exactly the same steps, just extracted in the call method of an authenticate user object. When I roll my own command object, I like to name the class as a verb, in this case, authenticate user. It initializes some optional config and some injected dependencies. That's a topic for another talk. Then there's a single method call, which takes some input and does some things before finally returning the output. While this code's okay, and it's certainly a lot better than doing the same thing in the controller, it's still not great. It's procedural in that it follows a fairly linear series of steps, but the nature of the process is that several things could go wrong. There could be no token, or an invalid or an expired token. The JWT gem handles this by raising an exception, so we need to rescue it, which happens non-linearly. Our eyes have to jump to the bottom of the method to see that getting handled. The token could be technically valid, but missing a key bit of data. Here, we need to be sure we have the subkey in the payload, so we return early if it's missing. The user could be missing or not found. They might have been deleted or had their account suspended. all three of these problems need to be handled differently with different HTTP status codes, maybe different response bodies or a redirect. The code provides no means for the caller to detect this, only that it returns a user or nil. We could handle that better with multiple return types or raising exceptions to be rescued, but that just means more conditionals and the flow of the code is broken further. Regardless, it's a good first step, and it'll get you a long way if you're careful about the size of these objects and how you compose them. Oftentimes, you'll want one command to call another, which calls another, and that can cascade in a way that's difficult to trace. Also, while it's helpful for encapsulating a small set of business logic in a single place, and it's definitely an improvement for testing, it doesn't really help much with error handling. If one of the commands in this long chain fails, how do you know which one? What's responsible for detecting that error and letting the rest of the system know? We'll skip ahead a bit and see if we can refactor the command object into a dry transaction. Don't worry, by the end of this talk, you'll understand what all this means. This is what a command object would look like in our application at Textus. First, notice how we've broken out all the implicit procedural logic into an explicit list of discrete steps. Each of these steps is run sequentially, and the output of one is passed to the next. Each can fail individually, and it just stops the transaction right there. None of the further steps are run. Each step also explicitly declares what the step failing means. Try means rescue those exceptions, and that's the failure. Check means it's a failure unless the step returns something truthy. And T means the step can't fail. Throw away the output of the step, kind of like the tap method in the Ruby standard lib. The really cool stuff happens over in the controller, though. When the transaction is called, it also takes a block that matches on the result of the transaction. Success means every step passed, and it passes the output of the transaction to the block. If any of the steps fail, then it calls the branch with the matching step name. The matcher code I have here is just a bit redundant. It's not really how we do it in our app, but I wanted to be explicit in this first example. Also, there's some magic going on at the top of the transaction. That include application import is leveraging a couple Dry.rb libraries to remove some of the boilerplate. That's another superpower of the Dry libraries, and I totally should do another talk on that. So how does all this work? We're going to take some detours, but we'll come back, and all this will make sense. Dry transaction is part of the Dry Ruby suite of gems that are interrelated, and they build upon each other into more advanced layers. Even if you don't use any of the gems, there's a lot of interesting ideas to dig through in the code. It'll probably make your personal coding style a lot better. The source code is fascinating. There's a lot of advanced Ruby tricks you can learn from reading through it. It's very much in the original spirit of the Ruby language itself, rather than the dialect familiar to developers who exclusively use Rails. Dry.rb is also the basis for ROM, the Ruby Object Mapper, which is an ambitious project to provide an alternative to Active Record, but not just for relational databases, but NoSQL databases, even HTTP APIs. It's also a pretty interesting project worth looking into. And also related is Hanami, which is an alternative web framework to Rails, but with a lot cleaner code and kind of sounder engineering principles from the ground. It leverages a whole lot of the Dry.rb libraries and ROM, and there's a lot of interesting ideas in there too. So what we're going to talk about is Dry Transaction. It's one of the higher level gems. It builds upon several others. You don't have to read all this. It's all in the README, but I'm going to paraphrase and point out the important parts. The term transaction is different from the one you're familiar with, a database transaction. Instead, this is a business transaction, which means it encapsulates some set of business logic within your application. It might involve several discrete steps, one after another, and it probably involves many different objects. If any of those steps fail, it'll stop processing, and the handling those failures is a first-class concern. The steps are declared in a DSL that lets you look at them from an abstract level without being coupled to how those steps are implemented. It doesn't have any state. It doesn't accumulate state as it runs. The same input should always produce the same output. It only has one public method, call, with some input. Errors are expected and handled as part of the normal application flow. They're not exceptional. And that's all from the README. And so to explore what a transaction is, let's start with a really simple one. It'll figure out what name we should use for a user given an ID. It has two simple steps. The first looks up the user in a database or something, and the second figures out a friendly name to call them based on the attributes of the user we found. Each step gets called in the order it's declared in the step DSL at the top of the class, and each step is expected to return a result. If it's a success, it gets passed to the next step. If a particular step returns a failure, the transaction halts there, and that failure is returned. I keep talking about result and success and failure. What does that mean? It's an idea that's borrowed from type languages like Haskell or Elm or Rust, and it's called a monad. A monad can be a fairly esoteric, abstract concept, but it's really simple. A monad is a monoid in the category of endofunctors. Yeah, I don't know what that means either. It's like a burrito or a taco or something, I forget. We're only going to look at the two simplest possible monads. So for our purposes, it's easiest to think of a monad as a set of wrappers that implement exactly the same API signatures. It just does completely different things based on what the wrapper is wrapping. The simplest monad is the maybe. It has two kinds of wrappers. One wraps a nil, the other wraps anything that is not nil. A maybe has only two possibilities, nothing or none, which is equivalent to nil, just or some value, which is not nil. The just is a container that holds the actual value, while the nothing replaces the missing value. In a strongly typed language like Elm, that code up there, or Rust, we can declare a function to have an argument as a maybe, and it'll be called with either a just or nothing. If we try to use that value directly, the compiler will yell at us. We can use pattern matching to unwrap the maybe and access the value to do something with it. Not only that, but the Elm compiler can detect if we didn't handle both possible types. If we tried to just talk to the value of the just and didn't do anything with the nothing, it gives you a nice error message. And you know how you have like a murder of crows and a pod of whales? You know what you call when you have a group of programmers? It's an argument. And because programmers can never agree on anything, all the different languages all have different names for the same monads and the same types, so there's a chart. I'm going to use the dry monad terminology from here on out. So why would you use the maybe monad? It prevents a class of errors that usually only present themselves in production after you've deployed and the site goes down. I'm sure everyone's seen this in Honeybadger, undefined method for nil. Since the maybe wraps the nil in something else, you can't ever accidentally call methods on the nil. Thus, you avoid this error, which has given programmers nightmares for generations. In Ruby, we can use the dry monads gem to get access to some of the advantages of monads. Dry monads provides a maybe monad and calls the two possibilities some and none. Since it's Ruby, both classes are duck types to quack like the same thing and respond to the same methods. They just have them implemented differently. Dry monads also supports Ruby 2.7 pattern matching, so we can implement the same thing as the Elm example on that earlier slide. We don't have a compiler to yell at us for passing in a string instead of a maybe, so it still raises the exception at runtime. But at least it happens in the normal general case and not some edge case where we forgot to have the test for it. In our contrived example, let's say we have the two methods that can both return nil. If the first works, we want to call the second. If the second works, then we do something with that value. And if none of them work, return a different value. In normal Ruby, we might write something like this. It's not great. When reading it, our eyes have to jump back and forth all over the place to figure out what's happening. We've got the code smell of those safe navigation operators on line 6 and the early return on line 10. There's also a bunch of landmines in here if we try to code golf this into fewer lines. Since both these methods can maybe return a nil, they're probably both great candidates for the maybe method, monad. So dry monad implements a maybe method with a capital M that takes a value or nil. If the argument is nil, then it returns none, and for any other value, it returns some value. We've modified find user to return a maybe wrapping the user. Friendly name can now safely assume it has a user, so we can drop the safe navigation operators. Both those attributes could be nil, though, so we wrap it in a maybe too. Finally, we use a series of methods that were implemented on the sum and the none objects, bind, fmap, or value or. If the monad is a sum, then the bind will yield the value, wrapping the block and return the result. If it's a none, it doesn't yield the block, it just returns itself. And that's how we know that friendly name will only ever be called with a user, because if the maybe was none, then it wouldn't be called. Fmap works similarly to bind and is short for functor map. In this case, it's a shortcut that will wrap the block's return value in a maybe for you. In bind friendly name, we did it explicitly, but here with fmap, we can just return the string. We also know that name in the block will always be there, because if it wasn't, our monad would be none, so it wouldn't call the block. Finally, value or is the safe way to unwrap the value. If the monad is sum, then it returns the value. Otherwise, it yields to the block and returns that instead. That means we know we'll always get a string out of this, even if find user or friendly name were to return nil. And we did it without any early returns or safe navigation. So how does this work? The implementation is actually pretty simple in Ruby. So if bind is called on a sum, it yields the value to the block and expects the block to return another monad. If it was called on a none, it doesn't call the block, it just returns itself. fmap works exactly like bind, but it wraps the result in a maybe, where, like in our case, where our block returned a string, we don't have to wrap it in the maybe ourselves. The last one is value or. It's the opposite of bind and fmap, and the safe way to unwrap the value in the sum. For none, it calls the block and returns that instead. It implements a few other methods, the inspectors like sum and none with questions, and you can check what kind it is. There's also an unsafe value bang method that unwraps the sum and returns the value, but it raises an exception if you call it on none. So it's really only useful if you've already verified that it's a sum. There's also a handful of other methods that are useful in other scenarios, and they're all documented on the Dry.rb doc site. But these really simple methods unlock some really powerful building blocks we can use to make our code simpler and easier to reason about. So let's look at the code again from before where we used them. Now you can see how those simple methods can easily be chained together to create what I think is some pretty elegant code. And once you get a feel for it, it's much easier to read and reason about than what we had before with the conditions and the early returns and all that. So sometimes, instead of just nil, our methods can provide more detail about what went wrong. So the maybe monad has a none, which doesn't tell us really at all why it was a nil. In these cases, we could use the result monad, which works almost the same way as a maybe, but in place of sum and none, we have success and failure. Success is basically the same as sum, it just wraps the value. A failure, however, can have a value of its own, which can be a symbol or a string, but it can also be any other object, like a hash or an error message or even an exception. So we can modify find user to return a result. In find user, we updated it to return a failure with not found instead of just none. But then since friendly name deals with nil, using a maybe is a convenient way to wrap that. But then we can pretty easily convert that maybe into a result using toResult, where the argument there is the value we use in the failure. Result mostly implements the same methods as maybe, so we can use bind and fmap and value or. And finally, we can use pattern matching to detect if we succeeded and if we failed, exactly how we failed, and generate a corresponding message. You can see how with two different failures, we're able to differentiate between the case where we couldn't figure out the user's preferred name and the case where we couldn't find the user at all, and provide a different error message for each one. If we go back to the simple transaction we had before our detour into the wonderful world of monads, hopefully this makes more sense now. Each transaction runs the step in order, as defined using the step DSL on lines 4 and 5 here. Each step must return a result of success or failure. If the result is a success, the value of it gets passed as the arguments to the next step. And if it's a failure, the transaction stops, and that failure is what's returned from transaction call. Finally, we can take the result we got from calling the transaction, whether it's success or failure, and do the same Ruby pattern matching on it to generate the message, just like we did when this was two separate methods we chained together ourselves. That's essentially all a transaction is. It's a pretty DSL for chaining together a bunch of methods that return a result monad. Since writing out success and failure would get tedious all the time, and that's totally not what Ruby's about, Dry transaction comes packaged with a few wrappers called step adapters. In fact, at TextUs, we hardly ever use the bare step method. We use these adapters instead, and we even wrote several of our own. We can use these adapters to simplify the implementation of the steps. The first is now a try, which returns a success if the first method returns something, and a failure if it raises the exception that's listed there in catch. If it raises any other exceptions, that exception escapes the transaction too. Since in active record, the find doesn't find anything, it raises an exception, we can catch that and turn it into a failure. Then the friendly name now uses map, which wraps whatever the method returns in a success. Another thing to note is that when using the implicit failures from the step adapters, the value inside the failure is no longer supplied explicitly, but is now inferred implicitly from the name of the step that failed. So whereas before find user failed with a not found, now it's going to fail with a failure find user. So back to that first authenticate user transaction. There's a couple more steps here. The check step only cares if the step returns something truthy or falsy. Truthy, and it passes the input straight through as the output. You can see how both the valid payload and the user methods take the same arg of payload. If the method returns false, then the step is a failure. The T step just runs the method, discards the return value, returning the original input as success. It's useful for like what we're doing here with some side effects like notifying segment or adding the user to the honey badger error context. So, having used transactions full time in our application for over 3 years now, I personally find this functional style of code to be really advantageous. Notice the lack of if conditions, guard clauses, rescues, and early returns. The code flow is very linear, and each step is isolated. When you're trying to understand part of the code to fix a bug, you only have to read a couple steps to understand what's happening. You don't have to jump through the file, bouncing back and forth, to try and understand where the different variables or helper methods are coming from. At a high level, you can just read the step names at the top of the file to understand what's going to happen in this transaction. You don't have to dig into each one if you don't need to. And if you do, you can just jump straight to the step method you're interested in. And from the step adapter being used, you can also tell at a glance what the code is expected to do. Is it a side effect? Are we checking for something? What exceptions are we expecting to be raised by this particular section of code? So now that we know what a monad is and how transaction steps work, let's dive into what I think is the best part about transactions and their secret weapon for making your code better: error handling. Oftentimes when writing code, you work on the happy path, and once that's done, you're reminded, oh yeah, this can sometimes go wrong. I guess I need to guard against all these nils and exceptions, and it becomes an afterthought. You'll probably even miss some of those cases until your code hits production. Since every step in the transaction returns a result, the transaction does as well, and we can do all the same things like bind and fmap helper functions or pattern matching. We initialize the transaction, we get a result. We can check the result if it's a failure and handle it, or continue on and set current user like a typical authenticating controller helper. But I've skipped over the most interesting part, and that's handling the actual failure. The transaction call method also accepts an optional block, which is a DSL for matching the result success or failure. I like calling the block variable on because it just reads really nice. When it's a success, the unwrapped value in the success, in this case the user, is yielded to the block, and we can do that same current user thing as before. The failure, like we saw before, is named after the step that failed, and we can decide to do something different based on that. In this case, we failed to decode the token for some reason, or the token didn't have the data we need. We can respond with a 401, and the response header is needed for the browser to make the token auth request. If the token was valid, but there was no user, like if it was deleted or disabled, we just want to respond with forbidden, because asking to authenticate again won't help. In our application at TextUs, we have a few controller actions that are trivial enough to not involve transactions, like mostly internal or utility endpoints. But the vast majority of our controller actions do some basic authorization using pundit and then immediately call a transaction to do the actual work. Nearly every transaction starts with a validate step, which we use dry schema and dry validation gems. This means we don't have to worry about or deal with permitted params from Rails. We also get much more granular validations where you can check types or massage the input, like stripping whitespace from strings. The transaction can also do extra checks of things. In this case, it's looking for duplicate contacts. We can handle that with a different error, or maybe we don't care. We just pretend that it worked. The transaction can also then do all the things we need, like enqueuing some background jobs to update a search index or post some webhook somewhere. We don't expect those to fail, so we don't handle it explicitly. But if something does, then it's handled on line 10. If you don't provide a step name to the failure branch, it matches all the other failures, similar to the else in a case statement. Another nice thing with the matcher DSL is that it's strict, like you find in a type language like Elm or Rust. If you don't handle all possible values in the monad, it'll refuse to run the transaction at all and instead give you this non-exhaustive match error. Here, we've handled the success, but not the failure, so it raises an exception. Since you get the exception, even if the transaction would return a success, like in a test, then it forces you to handle all those cases, making it a lot harder for them to escape into your production environment. Gotta hurry. My other favorite thing about transactions is how easy they make it to test them and your app that uses them. Because each step is defined at the class level, it's known to the transaction, And it has a list of all the steps that were defined with the DSL. This makes it possible to override the implementation of the step at runtime. In fact, you can use dependency injection to pass a whole new implementation of a step to the initializer of the transaction itself. Here, we've replaced the find user step, which did the DB lookup, with a lambda that just returns a failure. This causes the step to fail, which causes the transaction to fail on that step. It's a little contrived, but you can see how this can be really useful when a step involves making requests to a third-party service without having to resort to mocks or VCR. We're able to directly supply the transaction with a particular step implementation. We can check that behavior of the transaction directly. On line 4, we've defined some default arguments, in this case, an empty hash. On line 7, we initialize the transaction with those arguments, and on line 11, we verify that the transaction is a success. Then on line 15, we override the initializer arguments with a hash that has the step name we want to override as a key and the value of a lambda to call instead of that step. This lambda explicitly returns a failure, so our test on line 17 passes because the transaction fails due to that step failing. At Texas, we use this to provide various fake responses, valid or errors from third-party integrations that we have to interface with. It's especially great for testing things like timeouts or database errors that are otherwise hard to trigger when using mocks or stubs. All right, we're going to blow through this one. So Dry transaction all provides means to write your own step adapters and make them available to your transactions. The Dry transaction documentation goes into this. So, you know what, we're going to skip this slide. This is how you make one. It takes the operation, the step, and the input, and it returns success or failure. But here's some of the ones we wrote. We've got a merge step. So we found it most effective for all our transaction to work with input and output params of keyword arguments. So probably our most used step is this merge step. Here's what two similar steps look like, one using the built-in map and the other using the custom merge step adapter. So to help follow along, I added a comment of what the input keywords for each step are. The first step, user, needs to look up the user in the database, and since the map step blindly returns the output of that step to the next step, if we instead wanted to do something with one of their keyword args in a later step, they're gone. Instead, we capture the keyword args as a hash using the double splat notation, and then once we find the user, we merge it into the keyword args hash and return that step. So we found ourselves doing this so often, we extracted that behavior into the merge step, which removes all that boilerplate. You can see how it's used in the metadata step after the user step. The input of this step is the output of the previous user step, so we have the user keyword arg we can work with. We don't care about the rest, so we just ignore them with the double splat. Then we might need something to make an API call to look up some metadata, format it in a hash, and we're done. The merge step takes care of merging that hash with the input hash, putting it under the key of metadata, which matches the step name. Another thing that it takes care of is that the step does not return success. If it does a failure of some sort, the map step will happily wrap that failure in another success and just keep going. The merge step, however, if the step results in a failure, it'll return that failure instead and halt the transaction. Another thing we do is we validate the inputs of the transaction. So that earlier example in the Rails controller where we just totally ignored Rails permitted params and passed the params to unsafe H directly to the transaction. It's because the transaction itself had its own validation using Dry validation. I'm not going to get into the details of this. So yeah, we have that special validate class method that lets you inline the Dry validation DSL right there. The other interesting step adapters we have are use, maybe, and async. Since we have so many transactions, the use comes where we just want to call another transaction from this one. And if that transaction fails, then this one fails. But sometimes you don't always care if the transaction you're trying to call fails. And so we have the maybe step. And the transaction you're calling with maybe must have a validate as its first step, and the maybe will first call that validator without invoking the entire transaction. If that validation fails, we just skip it and continue on. If the validation succeeds, then the transaction invoked, and the overall success or failure becomes the result of that step. And then finally, the async works exactly like maybe, except it uses active job to enqueue the whole transaction as a background job rather than running it inline. This is great for background sync jobs, plus it does the same validation pre-check. So if there's nothing to do, it doesn't enqueue any jobs. So that's it. I know that was pretty fast, it was pretty dense, I barely scratched the surface, but I hope I got you more interested in learning more about functional programming and monads and Dry transactions. Thanks.